Today we are going to talk in some detail about how gases absorb infrared radiation. In the simple model we discussed earlier, we had assumed that the absorptivity to solar radiation is around 20% and the emissivity is around 0.95, and we did not elaborate how this was obtained. So today we will go into some detail about the complexity of radiation heat transfer in gases and how various gases like carbon dioxide, ozone, water vapor, methane contribute to the change in absorption of Earth radiation. So to begin with, you must have a law, okay? And the law that is well known for the last 200 years. This law in some books is called Beer's law or some other name, but I would say this is common sense. This law says that the change in intensity of radiation going in one direction, what we call directional spectral intensity in the first lecture, is proportional to the incoming intensity. So you can think of this as number of photons per square meter. So there are more photons in the path, of course there will be more absorption, right, or scattering. And it is also proportional to distance travelled. More distance you travel, you will encounter more number of molecules which can absorb or scatter, so your radiation absorbed more. And the proportionality constant is a property of the gas. This is called extinction coefficient, K lambda. So this relationship is very simple and follows common sense that the intensity of radiation should go down as you go through a gas, either because of scattering or because of absorption. It is proportional to the amount of radiation coming in and the distance travelled, and the proportionality constant is a property of that gas. Okay. Now we are going to resolve this extinction coefficient to two parts, absorption and scattering, and both have the units of meter minus 1, because in this equation you can see that intensities are both sides. If this is in meters, this has to be in meter minus 1 over meter. Now we will focus in this lecture only on the absorption coefficient. We will neglect scattering for the time being, because in the infrared region beyond about 4 to 5 micron, the role of scattering is limited. In the short wave solar region, scattering is very important. Now scattering causes a photon to change its direction. Okay. So photon, instead of going in this direction, goes in some other direction. As far as you are concerned, as you are focusing on this direction, the photon is gone, okay, but it is going to go some other direction. If the photon is absorbed, it disappears, okay, and becomes heat. So if you integrate the above equation without including scattering, we have a simple thing which all of you know from the solution of first order ordinary differential equation, which is that at a distance L from the origin, the intensity will decline by e to the power of minus a lambda L, assuming a lambda is constant. Okay. Now using this equation, you can define a directional spectral absorptivity, which we defined for opaque surfaces in the first few lectures. So the directional spectral absorptivity is nothing but the intensity at the end of that passage of the gas to the initial intensity divided by initial intensity. There is nothing but absorbed radiation by incoming radiation, same as what we did for opaque surfaces. Now by Kirchhoff's law, the directional spectral absorptivity has to be equal to directional spectral intensity. Okay. So we have an expression for both the directional spectral absorptivity and directional spectral intensity in a gas with the absorption coefficient a lambda and the length of the layer through which the gas is going is L. Okay. Now notice that A lambda has units of meter minus 1, L is meters. So A lambda L is a non-dimensional parameter, very important parameter in radiation. So if you describe the length of the passage of the radiation in meters, A lambda is 1 over meter. But suppose you want to include the density of the gas, then you can measure the length in terms of amount of gas per square meter as you go along. Okay? So that will be in kg by meter square. This is called mass path length, amount of mass along the direction per square meter in the perpendicular direction. So if you are going to measure the passage of the gas in terms of kg per square meter, then A lambda will be in meter square per kg, and this is called mass absorption coefficient. Okay? The other one is volume absorption coefficient, mass absorption coefficient. Now when you look up various textbooks and research papers, you must be careful how A lambda is defined, what units. Okay? So that's very important to keep in mind. Now the advantage of using A lambda as 1 over meter is 1 over A lambda is the mean free path of the photon. So 1 over A lambda gives you a good idea about the distance travelled by photon before it is absorbed. Okay? The concept of mean free path is well known from kinetic theory of gases. So radiation can follow the same logic, and we can define the photon mean free path as 1 over A lambda, in some way similar to what you must have heard about molecular mean free path, which is defined in kinetic theory. Now A lambda L is of course non-dimensional, whether you measure A lambda as meter minus 1 or meter square per kg. Okay? And A lambda L is called optical depth, and if it is much larger than 1, this quantity becomes very small and absorptivity approaches 1. Okay? On the other hand, if A lambda L is very small, there is no absorption at all, then you can expand this in a Taylor series, and then this quantity is proportional to A lambda L. So for a thin layer of gas, the directional spectral absorptivity is nothing but the optical depth, A lambda L. For an optically thick gas, the second term becomes very small, and A prime lambda approaches 1. And this is sometimes called saturation. What it means is that if you go long enough distance in a gas in a wavelength where it is absorbing strongly, beyond a certain point there will be no further absorption. Okay? So, but remember it is only in this wavelength. In an adjacent wavelength it can still absorb radiation. Okay? Now the reason why I am clarifying this, a lot of people who have not understood radiation well, they say that carbon dioxide is a strong absorber of the radiation emitted by the earth, which is true in a certain wavelength. So in that wavelength the what you call absorption band is saturated, and hence further increase in CO2 will not affect. So they will argue with you that we shouldn't worry about increase in carbon dioxide because it is already saturated. That is completely misleading. Yes, in certain wavelength the absorptivity approaches 1 and no further absorption occurs at that wavelength. But there are other wavelengths you will see nearby where carbon dioxide still absorbs, but not as strongly. So there absorption will continue to happen. So do not get fooled by the term saturation. That is true at that one wavelength where A lambda is very, very large. Okay? A lambda is not large everywhere. Remember that in gases the absorption varies very strongly with wavelength. If you move even a small distance in the wavelength space, 0.01 micron for example, you may go from A lambda of 100 to A lambda of 0.01, because that is the nature of gases absorption. It is very strongly varying with wavelength, and that is why you will see that in this course we will not be able to provide you an analytical expression for absorption, although we will show some approximations, but they are of limited validity because A lambda varies strongly with wavelength. When you want to integrate this equation over all wavelength to get total absorptivity, you have to do very careful integration along wavelength space because A lambda varies very strongly with wavelength. I will show you some examples today. Now, to understand why all this complexity occurs, you must know the basic physics of absorption. Okay? Now, absorption occurs because a photon is absorbed by a molecule and either electrons move from ground state to the upper state, that is called the electronic transition, or the electron moves from the ground state of vibration to the first level, that is called molecular vibration, or it moves from the ground state of rotation to the upper level, okay, in a two-level system. Now, it so happens the spacing of the energy levels in gases is such that most of the photons that are absorbed by gases have to be in the visible to initiate electronic transition. So, in the visible region like solar region, when a photon is absorbed, electrons move from a ground state to the next state. Now, we will focus mainly on infrared radiation, where the energy is much lower, h nu is much lower. So, the only transition we will talk about is in vibrational mode or rotational mode. Okay. Vibration has much higher energy level difference than rotation. So, most of the vibrational transition takes place in the region 4 micron to around 20 micron. Beyond that, it is only rotation. Rotation delta is much smaller, so it can only initiate transition at high wavelength around 50 to 100 micron. Okay. You can see the energy here mentioned in joules. You can see the difference about 10 to the power of 5 between rotation and electronic transition. So, when there is electronic transition, the photons have to be in visible or ultraviolet. When there is vibrational transition, the photons have to be near to far infrared, between 1 micron to let us say 20 micron, and changes in rotational result when you are in far infrared or microwave. But you must remember that whenever there is vibrational transition, there also will be some rotational transition, because a photon comes in and is being absorbed by a vibrational mode of molecule, and the photon has slightly more energy than what is required for that transition. The additional energy is used to do a rotational transition. It is like you are giving money to somebody and you have to give him 1 rupee and 50 paise. The 1 rupee is equivalent to the vibrational transition and the 50 paise is equivalent to rotational transition. Small change is rotational, the big value is rotational. So, whenever there is vibrational transition, you will always have rotational going along with it, and when you are electronic, it will be accompanied by vibrational rotational. So, it is very complicated. Electronic transition in the visible is a very complex spectra. We will not discuss that in this course. So, carbon monoxide, nitrous oxide, water vapor and ozone exhibit pure rotational spectra because they have permanent dipole. So, you require a dipole difference in electron as the molecule rotates for it to interact with the electrical field. Imagine the field coming in and this molecule rotating, let us say carbon monoxide. To interact with the field, the dipole moment has to change during rotation, then it can absorb the photon and rotate faster. Okay. Now, carbon dioxide and methane do not have permanent dipole moment, so they do not have pure rotational mode. But when there is vibration, the molecules oscillate and they have combined vibration rotation mode. Okay. So, a molecule must possess a permanent electrical or magnetic dipole moment for it to interact with the electrical field. Okay. And that is why the two major gases in the Earth's atmosphere, nitrogen and oxygen, do not absorb almost any radiation in either the visible or in the infrared, because they do not have a permanent dipole moment. Okay. And so does argon, which is an atom. Okay. So, this is a peculiar feature of the Earth's atmosphere, that nitrogen, oxygen and argon, which constitute 99.9% of the Earth's atmosphere, they do not contribute directly to the absorption of photons either in the visible or in the infrared. Okay. And that is why the Earth's atmosphere is so sensitive to small changes in minor gases. Remember, carbon dioxide, water vapor, ozone, methane are minor gases. Carbon dioxide is in hundreds of parts per million. Methane is in around 1 part per billion, 1 part per million. And if you look at chlorofluorocarbons, which we will talk about, they are in parts per billion. So, and ozone is also in parts per billion. All these gases with such minor contribution to the composition of the Earth's atmosphere, they have a big impact, because the three major gases which constitute 99.9% do not absorb or emit any radiation in the visible infrared. So, this is what makes Earth's atmosphere so sensitive to minor gases. This sometimes is not appreciated by many people. They always assume that minor gases cannot play a major role in the Earth's climate. Now, all this skepticism changed when we had COVID-19 4 years ago, when people realized that a virus whose scale is nanometers had a big impact on our life. Whole economies were closed down. People were asked to stay at home, all because of minor virus which you could not see. It is so small, had a big impact. So, you must remember that on the Earth, many minor things which we cannot see have a major impact on our life. So, this is a lesson we got from COVID-19. Now, here is a pictorial depiction of energy levels in the typical molecule. Is the ground state of electronic, the excited state, and then we show various vibrational modes and then rotational modes. So, you can see the vibration level difference is smaller than electronic. That is, electronic requires a visible photon, while vibration can absorb a IR photon, and rotation is even smaller. So, it requires photon at much higher wavelength or low frequency. So, this is the order of things. Far infrared is where rotation change will occur easily. Near infrared is vibration, and mostly visible, and near infrared is electronic. Okay. The absorption spectrum of a molecule is determined by all allowed transition between these energy levels, depending on whether a molecule exhibits sufficiently strong electronic or magnetic dipole moment okay, to interact with the radiation field. Now, we are going to only focus on infrared absorption. So, I am showing here the vibrational rotational transition, in which you have a ground state here and the upper state here of vibration, and within that there are many rotational states along with this ground state and upper state. Okay. Now, if there is pure vibrational transition, so called Q branch, that is no zero, there is no rotation change, no vibration change, that is called Q branch, and for many molecules this branch is not there. That transition is forbidden by quantum mechanical rules, but some molecules have it. Now, if the vibrational mode is accompanied by a rotational mode, then you have all these transition called the P branch, which are at a lower frequency, where the molecule goes from lower vibrational mode to higher vibrational mode, but rotation transition is from a higher mode to lower mode. Okay? That is why the frequency is lower than nu 0. But if the photon coming is at a frequency higher than nu 0, it will transition the molecule from the ground state to first state of vibration and from the ground state to upper state of rotation also. So, depending on the frequency of the molecule, it will find the right transition in which delta E equals h nu. Okay? That is how it occurs. Now, this can be shown in terms of absorption spectra as observed in the laboratory. Okay? So, each of these is a line in which photon was absorbed. This is the R branch, this is the P branch corresponding to this figure. Okay? And there is no Q branch in this particular example. Okay? This is how the spectra look like when you do a laboratory measurement. But the actual spectra can be more complicated. The problem in the real world is that suppose you take carbon dioxide. When you talk about carbon dioxide, the dominant carbon dioxide we have in the earth atmosphere is C16O218. That is, the atomic weight of carbon is C12O18. The atomic weight of carbon is 12 and that of oxygen is 16. So, 12 and 16. Okay? That is the most dominant. But when you take any sample of air in your room, it will also contain other isotopes like carbon 13, carbon 14 or O17, O18. So, when there is a mixture of isotopes in a gas, then the spectrum gets more complicated, because C12 O16, CO2 containing C12 and O16 will have one spectrum. One is having C12 O17 will have a slightly shifted spectrum, because the atomic weight of oxygen has gone up. Okay? So, when you take the real spectra of gases, because of the presence of isotopes, the spectra gets very complicated. If you want to get a simple spectra, you have to order from a company completely pure gas containing only C12 and oxygen 18 molecules. Okay? So, since the number of molecules of other isotopes is very small, it does not have too much impact on our study of greenhouse effect. But when you look at a spectra, if it looks a little noisy, there are many more lines than what we have shown here. You should be cautious. You should ask yourself whether did they have a pure sample or not. Okay? Now, from quantum mechanics, the change in the rotational mode is -1 in P branch and +1 in R branch and 0 in Q branch. And a typical transition for vibration is in the frequency range 600 to 1000 centimeter minus 1 in wave number, while rotation is 1 to 500. You can see they are not overlapping. Okay? This is much smaller than this. But whenever this occurs, this will also happen. But when this alone occurs, this will not happen, because the photon frequency is too low, so it cannot initiate a vibrational transition. Okay? So, when the molecule is in the lowest vibrational state, the rotational state need not be the lowest. It can have many other states as shown in the figure I showed here. So, the molecules can be somewhere here, ground vibrational state, but state of level 4 in rotation. Okay? That is quite common. Now, the energy at any level for rotation is governed by this formula from quantum mechanics. J is j plus 1 times Planck's constant by 2 pi the whole squared by 2 into I, where I is the moment of inertia. Take a carbon monoxide molecule CO and it is rotating around the vertical axis. Then you have to find the moment of inertia depending on the mass of the photon and the distance of the mass of the molecule and distance of the carbon and oxygen atom from the center. Okay, that's how I calculate the moment of inertia. Okay, and when this changes delta J, you get the change in the energy, and this is written as frequency is equal to 2b into j plus 1, and b is a constant determined by Planck's constant, the speed of electromagnetic radiation, and the moment of inertia. So, the moment of inertia determines what will be the quantum of the rotational energy transition and hence the frequency. Okay. And b is called the rotational constant. Units is in this case centimeter minus 1 in the wave number space, or you can have it in frequency. Now, let us go to vibrational transition. Okay. A typical example given is vibration can have many modes. I will talk about that and come back. Let us look at the modes and then come back to this. Yeah. So, this mode is called the symmetric stretching. The two oxygen molecules are going in and out symmetrically about the carbon atom in the center. There is a symmetric stretching. It occurs at around 7.2 micron in the absorption band. Okay. This is not that active. Then you go to asymmetric stretching, where it is still stretching, but not equally in both directions. So, when one molecule is moving to the left, other is going to the right. So, it is not symmetric like the previous case. Okay. The previous case was symmetric, both are going out, both are going in. Here one is going out, other is going in. So, it is asymmetric, it is very active. There is a 4.3 micron band in the near infrared, and this contributes to some absorption. But remember, this is not close to the peak of the black body spectrum of Earth's emission. So, it is not that strong in greenhouse effect. The last one is the bending mode, where the oxygen molecules are bending, not stretching. This is a very important mode, and it occurs around 15 micron band, and it has a strong absorption. And since 15 micron is close to the peak of the Earth's emission, it is the most important absorption band for carbon dioxide for greenhouse effect. So, greenhouse effect contribution of carbon dioxide comes mainly from this mode. Okay. But remember, this mode will go along with rotational modes of carbon dioxide. So, having shown this mode, let me just go back to the symmetric stretching here, 2.7, bending 15 micron, bending in water vapor is 6.3 micron, asymmetric stretching is 4.3 micron in carbon dioxide and 2.7. All these numbers come from this equation. This equation says photon absorbed h nu depends on the quantum number of the transition, Planck's constant, bond strength, that is the force which is holding the two oxygen atoms to the carbon atom. That force, when you think of the two oxygen atom carbon atoms as a spring mass system, that is the spring mass constant K bond, and the reduced mass, that is effective mass, which has a mass of oxygen and carbon together. So, this was controls the value of the frequency. Okay. From basic spectroscopic data, we can find K bond, we can find MR. All these are tabulated in all books, and these are known, well known, and so we find the frequency. Now, this is the equation of frequency. The bond strength, the two masses which are vibrating, M1, M2, and Avogadro's number, which is a part of quantum mechanical calculation, and M1, M2. This is reduced mass and this is the spring constant of the vibrational mode. Okay. This for a diatomic molecule. Now this already shown, I will move on. The 3 modes of carbon dioxide. So vibrational transition have a large energy than pure rotational transition, we saw that, and both stretching and bending have infrared absorption bands, and stretching are at high frequency corresponding to bending. Okay. Now here are examples in which the first 2 do not contribute any absorption bands because they have no electrical dipole. There is a small magnetic dipole which is not strong enough to affect our greenhouse effect, but it has some relevance to remote sensing. Okay. So we will not talk about it in this course. Carbon monoxide is an asymmetric molecule. So when it rotates or vibrates, it has a dipole moment. So it has an absorption band. Carbon dioxide is a linear triatomic molecule. It has no permanent dipole moment in this mode, but along with rotation it can contribute. Nitrous oxide, because remember it is asymmetric, carbon dioxide is symmetric, nitrous oxide asymmetric because the 2 molecules on either side of nitrogen do not have the same mass. So it is a permanent dipole moment. Then you have water vapor, which is called the asymmetric top molecule compared to the symmetric carbon dioxide, and it has a permanent dipole moment, and so it has lots of vibrational modes. You have ozone, which is similar to water vapor, asymmetric top, so it has permanent dipole moment. Then you have methane. Okay. It has carbon in the center and 4 hydrogen molecules. It has a permanent dipole moment. Okay. So again this is shown in this cartoon in terms of the stretching mode, the bending mode. The bending mode has 2 different planes. It can bend in the plane of this page or perpendicular to it, but they are called degenerate, but they do contribute. Huh? Okay, they have same energy. This is asymmetric stretching. You saw the animation of that. So here is the display of the symmetric stretching mode and the corresponding wavelengths, and that of water vapor. Bending mode 6.3 micron band, very important absorption band of water vapor, and very important absorption band of vibration of carbon dioxide. Asymmetric stretching 4.3 is not as strong as the 15 micron band, but it is important, and the asymmetric stretching of water vapor is 2.66 micron band. It does not have influence on the greenhouse effect because it is too far close to the solar region, but the 6.3 micron band is important. Okay. So I will, and this methane, which is also important. It has an important band at 7.7 micron, close to the peak of the Earth's emission. And ozone has 3 bands around 9 micron, 9.6 micron and 14 micron. Okay. And carbon dioxide we already saw 15 micron, 4.3 and 7.5. Water vapor already, this is a different way of showing it, and this is the animation of the modes of water vapor, bending and symmetric stretching. And this is nitrous oxide, a linear molecule. Now I will stop here and continue about absorption lines in the next lecture.